Hello, this is Peter Carter, a video for the Climate Emergency Institute. I'm making this video early in September 2021. It's a long climate change science data video, and it's long because it takes a look at all the climate change indicators, of which there are many. It addresses the most important question: how fast is the climate being changed? And could climate change today be tracking the worst case scenario? The conclusion of this exercise is that the climate is being changed faster than ever, tracking the worst case scenario. There's reason to think that this is the case. On the 22nd of September 2019, the World Meteorological Organization, the WMO, published a climate change report covering the years 2015 to 2019. And the headline for the press release was "Climate Change Accelerates." On the 19th of April 2021, the WMO issued its report on climate change in 2020, saying the pandemic-related economic slowdown failed to put a brake on climate change drivers and accelerating impacts, according to this report and an extensive network of partners. Global warming, global surface average temperature increase for 2020. In January of 2021, Copernicus for the European Commission issued its report on temperature in 2020, finding it was the warmest year on record for Europe, and that globally 2020 tied with 2016 for the record warmest year, and this was at a global temperature increase from pre-industrial at 1.25 degrees C. There are two illustrations from this report. The one on the left here is the global average temperature increase, and there you see the tide records of 2016, 2020, and then there's this decadal global mean surface temperature change, and this clearly shows an accelerating rate of global warming, of global average temperature over this period up to 2020. What we are doing here is a worst case scenario assessment from global climate change indicators. We will be comparing the historic observed, that is recorded, data on a whole variety of climate change aspects. So global surface temperature increase, warming, atmospheric greenhouse gases, changes to the ocean, changes to the Arctic, and we will be matching that trend to climate model projections of those particular aspects. What are global climate change indicators? They are direct causes and direct effects of atmospheric greenhouse gas pollution, and there are a great many of them. Here is an example from the IPCC's 2019 special report on the cryosphere and the oceans. Cryosphere, the frozen parts of the planet, snow and ice. And as you can see, there are many such indicators here, and we use them in this study. You're looking at recorded observation data, which is definite, and then computer model projection of future, near future being most important, changes in the indicator. And you can see here that there is a projection in red and a projection in blue. The red one is the worst case scenario, and the blue one is the best case scenario. So in this study, we are seeing how the worst case scenario matches with the present observations of the particular indicator. These are the climate change indicators that we'll be looking at, and this covers all the climate change indicators available: global emissions, atmospheric greenhouse gas concentrations, radiative heat forcing, global surface warming, ocean heat, ocean acidification, ocean deoxygenation, sea level rise, Arctic heating, melting ice, the Greenland ice sheet, and the Antarctic ice sheet. This is the indicator that's routinely referred to, but it is only one indicator. This is global warming, or global average, that is average of land and ocean, surface temperature increase, And this example is from the IPCC 5th assessment in 2014. The black is the observed or recorded surface temperature increase dating from 1900, and then these are the computer model projections. This one, the higher one in red, is the worst case scenario called RCP 8.5, and this is the one which we're going to be looking for and looking at. And this is the best case scenario called RCP 2.6, and this scale here is the global temperature increase from pre-industrial, or 1850 to 1900, and that's what we'll be using for this exercise because that correlates with our 2 degrees C, our old 2 degrees C limit, and our present 1.5 degrees C limit. I'm starting with recent published papers that point to the worst case scenario. This is a shocking finding. This is from a NASA press release June the 15th of this year, 2021, and a joint NASA NOAA. NOAA is the U.S. National Ocean and Atmospheric Administration, and their study finds that Earth's energy imbalance has doubled. Of this doubling in energy balance, or doubling in heat added to the climate system over just the past 14 years. There is the heat uptake in Wilms per square meter from 2005 up to 2019. A 2017 United States National Climate Assessment Climate Science Special Report, that's the federal government, that the observed increase in global carbon emissions over the past 15 to 20 years has been consistent with higher scenarios. That is RCP 8.5, which is the very highest scenario, and they say that with very high confidence. They go on to say continued growth in CO2 emissions over this century and beyond would lead to an atmospheric concentration not experienced in tens of millions of years. The present-day emissions rate of nearly 10 gigatons of carbon per year suggests that there is no climate analog for this century any time in at least the last 50 million years. This is a key paper, if not the definitive paper, on whether we're tracking the worst-case scenario, RCP 8.5. It was published in August of 2020. The title of the paper, RCP 8.5 Tracks Cumulative CO2 Emissions. Another paper published, Ice Sheet Losses Track High-End Sea Level Rise Projection, published in 2020. And a quote from the paper, the Greenland and Antarctic ice sheets are tracking the UN's worst-case scenarios for sea level rise. I'm just going to show our simple, straightforward methodology. Here's a methodology using, as an example, global warming, global average surface temperature increase. So first we find a projection of the worst case IPC scenario, RCP 8.5, for the particular indicator we're looking at. And in this case we use the IPCC. Most of our examples we use the IPCC, and this is from the 2014 fifth assessment. This one here, the higher one, the red and pink, this is the worst case 8.5. Then we get the latest actual observed or recorded present day result for the climate change indicator. And in this case, the last result for global warming was 2020, put at 1.2 degrees C by the WMO, World Meteorological Organization. So now we take this graph that goes up to 2100 and we focus it down to the present day. So there it runs from 2000 to 2050. So then we find what is the IPCC RCP 8.5 at 2020, at year 2020. So you can see that it's 1.15 degrees C. Again, this scale, temperature scale here, is from pre-industrial. So the result is that the actual present day for 2020 temperature increase is 1.2, and the RCP 8.5 worst case is 1.15. So the WMO quote here is from the 20th of April 2021, State of the Climate in 2020. So we're starting off, of course, looking at emissions. This is a good image of global emissions of all the greenhouse gases, which is called global CO2 equivalent emissions. We use the CO2 equivalent because that's carbon dioxide and the other greenhouse gases. This graph is from UNEP, and it shows emissions in gigatons of CO2 equivalent from 1990 up to 2019. As you see here, fossil fuel CO2 is by far the biggest contributor. Next is methane, CH4. Then next is nitrous oxide, N2O. They are the main greenhouse gases. This is where we get the latest data, the latest result for global CO2 equivalent emissions. It's from the Netherlands Environmental, PBL, and they produce an annual report on global greenhouse gas emissions, and this one was published in 2020. So it's greenhouse gas emissions for 2019, and the quote here is the 2019 global greenhouse gas emissions amounted to 57.4 gigatons of CO2 equivalent. So there's our number, 57.4 gigatons of CO2 equivalent. So here I've simplified that previous diagram just to show the total of the greenhouse gas emissions, and 57.4 gigatons of CO2 again. In this case, it's clear that emissions are accelerating. Here's where we take that number and compare it with the projection for the worst case scenario of global CO2 equivalent emissions, and that we obtain from this paper here. It's a paper published in 2011, but it gives us the projections accurately. And this is the graph from this paper showing the RCP scenarios for CO2 equivalent emissions. And focused, we can take the portion of the graph from 2000 up to 2040, put in 2019 there, and the 2019 projection of CO2 equivalent emissions, as you can see, is 52 gigatons. So the worst case projection, which is in brown here, is 52 gigatons. This gives us our result. The actual present day 2019 emissions, 57.4, and the worst case scenario, 52 gigatons. So we're tracking the worst case scenario on CO2 equivalent emissions. This is a very relevant bit of recent information. It complicates the issues a little bit that we had COVID and we had this pause of industrial activity and consumer activity, and this shows CO2 emissions from fossil fuels provided by the International Energy Agency. And this is a report in which they explained and showed that fossil fuel CO2 emissions have rebounded very, very rapidly, practically up to their pre-2019. And so we can still certainly assume from this that we'll be tracking the worst case emissions. Next is atmospheric greenhouse gas concentrations. Now we're going to be using, of course, the atmospheric CO2 equivalent concentrations in the atmosphere. Because this image is particularly clear, I'm starting with it, and it's from the Australian Bureau of Meteorology and published in 2021, the State of the Climate in 2020, and it gives the atmospheric CO2 equivalent in 2019. Their result is CO2 equivalent of 508 ppm in 2019, which actually is slightly higher than the NOAA's estimate, which we're going to look at next. Here is the atmospheric carbon dioxide concentration from 1900 accelerating rapidly, and here is the atmospheric CO2 equivalent also accelerating rapidly, particularly over the past decade. And you see there's a appreciable difference between CO2 and all the greenhouse gases, the CO2 equivalent, which is considerably higher than CO2 alone. This is from NOAA in the States. I think this is the single most important source for quickly assessing global climate change. It's called the Annual Greenhouse Gas Index, and why it is the most important one is it provides us with two key data informations. One, the atmospheric CO2 equivalent, and the other, the radiative heat forcing, the amount of heat added to the climate system by our greenhouse gas emissions piling up in the lower atmosphere. The blue here is the CO2 alone. The black is the CO2 equivalent, all the greenhouse gases. The red one is the radiative heat forcing, which is given by NOAA as what they call the greenhouse gas index. And this is simply the radiative forcing compared to 1990. Here's the simplified NOAA image showing the CO2 equivalent only, and their result for CO2 equivalent in 2020 is 504 parts per million. Quotes from the report: in terms of CO2 equivalents, the atmosphere in 2020 contained 504 ppm, and we've turned up the warming influence from greenhouse gases by 47% since 1990. And that, of course, is huge. Now we determine if atmospheric CO2 equivalent is tracking the worst case scenario using the NOAA number of 504 ppm in 2020. There's that graph that we've just seen. And for comparison, we have a source from the EPA, Climate Change Science, the Future of Climate Change, published 2017. This gives us the atmospheric CO2 equivalent for all the RCP scenarios. In this case, the worst case highest scenario, RCP 8.5, is in black here. So we cut this down to the present day from 2000 to 2040, and we have 600 ppm of CO2 equivalent up here. First of all, to find out what the 2020 RCP 8.5 would be, it's 480 parts per million. Our actual CO2 equivalent in 2020 was 504 parts per million. So definitely tracking the worst case scenario. Now we get to global warming. Is global warming tracking the worst case scenario? Global warming is global average, that is land sea surface temperature increase. And here we've got three examples from the IPCC for a good degree of certainty of our finding. This graph we've seen before as the example of our method. So this is the worst case scenario, RCP 8.5, and it's from the 2014 IPCC fifth assessment. And this temperature increase here is from pre-industrial. For the actual temperature increase, we use the result from the WMO, the World Meteorological Organization. Global warming in 2020 was 1.2 degrees C. And that's above pre-industrial, the 1850-1900 baseline, and WMO State of the Climate in 2020, published April 2021. So with that in mind, we cut this graph down here to the present day as 2000 up to 2050, and we see what the worst case RCP 8.5 scenario would be in 2020. And it is projected to be 1.15 degrees C. So we've got the actual global temperature increase in 2020, 1.2 degrees C, and the RCP 8.5 projection from the AR5 in this example of 1.15 degrees C, so tracking the worst case scenario. Here's the second example. It's also from the IPCC fifth assessment. It's directly from a research paper published by a group of climate experts, and this is the source from the AR5. It's figure 1240. And again, we've chosen this because this is the only other global temperature projection that includes the pre-industrial baseline. So we've cut this figure here down to the present day, and what we find is exactly the same as we found on the previous example. The 2020 RCP 8.5 is 1.15 again, and actual WMO was 1.2 again. So confirmation that global warming is tracking the worst case scenario. This is the third example, and it's a little different and particularly interesting. This is from the IPCC 2018 1.5 degrees C special report. And this rather complicated image, which I've simplified, I'll show in a second. This shows accelerating global warming, and this gives short-term model projections up to 2030, 2040. There are two different model projections here. Here is a simplified version of that graphic, just to show the red is the actual recorded global temperature increase, and there's a yellow one behind here, which is the this is a clever from a clever paper and project, ongoing project, in which the scientists have isolated the global warming caused by our greenhouse gas emissions from other extraneous events that cause these up and downs of the global temperature record. And again, I've kept the two model projections in. Here it is in large size. It's from 1850, and this goes up to 2050. This projection from the 1.5 degree C report is based on the worst case, RCP 8.5. So the global warming in 2020 we know is 1.2 degrees C, which is here, which is right there. So from the 1.5 degree C report, with the model projections, we are also tracking the worst case scenario. It's just between the two models and a little bit towards the highest model. This is the 1.5 degree C level, which is again around 2030, and this is the 2 degree C projection, which is possibly considerably earlier than 2050. This is what I was mentioning, the study that isolates the global warming caused by our greenhouse gas emissions, and this is online and updated. It's called the Global Warming Index. It's from an original paper from Oxford University climate experts, and this update is April of 2021. So this global warming index on the 15th of December 2020 was 1.21 degrees C. You can see very clearly how the global warming is accelerating from 1860, but also how it's accelerating very recently in the past 10 years. They also include the cumulative atmospheric CO2, which we've seen already, and we've seen the paper that has concluded that this also is tracking the worst case scenario. Next, we come to the oceans. But first, just to mention that the oceans, the world ocean, is by far the largest and most important component of the climate system. We're starting with ocean acidification because this is the direct result of the industrial carbon dioxide emissions. Also contributing to that, of course, is deforestation. Again, we're going to start with the illustration and example from the Australia Bureau of Meteorology, State of the Climate in 2020. Now, this is the diagram and the result that they provide, and this is pH, hydrogen ion concentration. Whenever we look for ocean acidification, what we'll find is pH. pH is the inverse of ocean acidification. So the quote from the Australia Bureau is that the rate of decrease in pH has accelerated to over 0.02 per decade, more than 5 times faster than from 1900 to 1960. This current rate of change is also 10 times faster than at any time in the past 300 million years. So the ocean is being acidified by carbon dioxide emissions at an extreme, unprecedented rate. So if we simply inverse this graph, we see relative acidification and see how the acidification is accelerating. This is the record from the NOAA, this being North Pacific seawater. The one that we just looked at was seawater around Australia. The red shows accelerating atmospheric CO2 concentration, and the green is seawater PCO2 content, and this decreasing track here in blue is the seawater pH, the inverse of acidification. And the result here in 2020 is 8.05. For confirmation of the 8.05 result for ocean pH, we go to the Japan Meteorological Agency, their update on pH being the 12th of February 2021. The various colors apply to the various locations north of Japan. The pHs are here. Declining pH, again meaning increasing ocean acidification, and as you can see, the pH comes out to 8.05. To determine the RCP 8.5 worst case projection of ocean acidification, that is ocean pH, we've taken this IPCC 2014 fifth assessment from Working Group 1. This is figure SPM 07, and it shows a pH declining, and this is historical. This is the best case scenario, RCP 2.6, and here is the worst case, RCP 8.5. Here we have cut it down to the present day. RCP 8.5 pH we find is 8.06 there, and for comparison, our actual 2020 pH is 8.05. So there we are, and ocean acidification is tracking the worst case scenario. The next climate change indicator is ocean heat, expressed by the science by the term ocean heat content. In 2019, the IPCC published a special report on the oceans, actually a report on the oceans and the cryosphere. And we see the result of the observed ocean heat up to nearly 2000, and then projections to 2100 for the worst case and the best case scenario. Cutting this down to year 2000, cutting this down up to year 2020, we can see that the best case and the worst case scenario for ocean heat have not yet diverged. However, ocean heat is definitely accelerating. This is the latest data from NASA, from their climate change vital signs, and the most recent ocean measurement was December 2020. This is from the Australia Bureau of Meteorology, their 2021 report, State of the Climate in 2020, and here we see ocean heat graphed plotted over the full ocean depth, and it is clearly accelerating. The scientists estimate that the ocean heat is equivalent to the energy explosion of 5 Hiroshima atom bombs every second of the year. This is the most recent paper published on ocean heat content, published in 2021 by L. Cheng. Title of the paper: Upper Ocean Temperatures Hit Record High in 2020. This is the record published in the paper, and I think you could see here that the ocean heat is accelerating. I've just copied it and put a smooth line through it to make it more obvious that it is accelerating. Here is the table of the ocean heat correlated with the years. 2020 was the record at 234 zetajoules, and that's a big jump from 2019 at 2014 zetajoules. This is an illustration copied by The Guardian, in which you can see more readily that big jump in the past year of the record. This paper shows that ocean heat content actually is tracking the worst case scenario, and it shows that there's a huge difference between the amount of heat that has been added to the southern hemisphere and the northern hemisphere. The southern hemisphere has taken 90% of the heat. Now, this paper correlated the heat content with the RCP scenarios, and here's the RCP 8.5 worst case there, and that's the actual heat content. This is from the supplement to the paper, which shows the observed recorded heat content with the RCP 8.5. There's the original, and I've cut that down so that we just see the observed recorded ocean heat content compared to only the worst case RCP 8.5 scenario. There's the global result. So the ocean heat is practically tracking on the worst case scenario, and this is the southern hemisphere ocean, which is way above the worst case scenario. Next indicator is marine heat waves, a relatively new phenomenon. A paper published in 2018 found that marine heat waves globally have increased 54% from 1925 to 1960. From 1925 to 2016, a paper longer and more frequent heat waves over the past century. This shows marine heat waves from 1950 through to the present time and projected to 2100. It's from the 2019 IPCC Special Report on Oceans and Cryosphere, and it looks like this is tracking the worst case scenario. This is the original image, and here it is cut back to 2050, and the vertical axis here is a multiplication factor of marine heat waves. So in view of that, it definitely looks like marine heat waves that have increased recently very fast are tracking the worst case scenario, RCP 8.5 again. Sea level rise next. The sea level is rising for two reasons. First, the thermal expansion of the ocean water, and secondly, the melting of land ice. This is from the Australian government, their State of the Climate in 2020, published in 2021. And you can see here that the sea level rise is accelerating, and the Australian report says it is. This shows two other sources of sea level rise. The top one here is NASA's Climate Change Vital Signs up to January of 2021, and below from the also United States National Ocean and Atmospheric Administration. The special report by the IPCC on the oceans and cryosphere does actually state that the sea level rise has accelerated due to the combined increased ice loss from the Greenland and Antarctic ice sheets mainly. Mass loss from the Antarctic ice sheet over the period 2007 to 2016 tripled relative to 1997 to 2006, and Greenland ice loss doubled in the same period. Here we are using the IPCC 2014 fifth assessment on sea level, which shows the worst case scenario, and comparing that with the latest data from NASA, which we've just seen. Here it's been cut back, as the IPCC record has been cut back to 2050 and cut down to 0.2 meters, and that shows us that the accelerating sea level rise looks to be tracking the worst case scenario. Ocean deoxygenation. Ocean deoxygenation has two factors. One, the warmer the surface water, the less oxygen the oceans absorb. The increasing heat content of the oceans is the big reason for deoxygenation. This is from that IPCC 2019 special report on the oceans, and this is the record from 1950 projected to 2100. This shows the change in ocean oxygen as a percentage below the zero level there relative to 1986-2005. So here is the focused view, and it's very clear, definite, that the decline, the percentage loss of ocean oxygen is tracking worse than the worst case scenario in this case. On to the Arctic, and first, Arctic temperature increase. The Arctic temperature is amplified from global warming because of the amplifying feedback of the loss of Arctic summer sea ice. We're looking now at the NOAA, their last Arctic report card of 2020. This is an annual report, and here we see the global temperature increase in black and the Arctic temperature increase in red from 1900 up to 2020. Here I've cut it back to 1980 to 2020. You can see from about the year 2000 the Arctic amplification of global average warming really starts to kick in. The rate of Arctic temperature increase is accelerating faster than the accelerating rate of global temperature increase, and that is faster and faster as you see the gap increasing between the Arctic temperature increase and the global temperature increase. The Arctic was accelerating at double the global warming average, but now it's accelerating 3 times faster. This is the last report from AMAC of 2021, and that's the Arctic Monitoring Assessment Program. From 1971 to 2019, the Arctic warmed 3 times faster than the global average. There you can see a polar view of the Arctic. There's Greenland, there's Scandinavia, and Siberia over here, and you can see that this Arctic region is warming very, very fast. The Arctic heating is abrupt, global heating is abrupt, and it is tracking the worst case scenario. A paper published in 2020 called Past Perspectives on the Present Era of Abrupt Arctic Climate Change took a look at the worst case scenario, RCP 8.5, for the Arctic with respect to the rate of Arctic decadal warming. So here is the observed Arctic temperature increase up to 2018. That big red area there is where the Arctic has been warming the fastest. That is the Arctic Ocean region adjacent to Siberia and Scandinavia, which is warming faster than any other region in the Arctic. And this shows the Arctic decadal increase, temperature increase per decade over the worst case scenario. This recorded trend is certainly as fast, and it's faster than this as published in this paper. Next we have melting ice on the planet. This was covered for the first time in total and distributed amongst the various ice sources on the planet in a paper called Review Article Earth's Ice Imbalance, published August of 2020. The record here starts in 1995 and ends at 2017. This is the ice mass change from zero at this 1995 point. What we can see is that glaciers, Greenland and Antarctica mass changes are declining at an accelerating rate. The glaciers is the deep purple, and then the next two purples are Greenland and Antarctica. The Arctic sea ice is the top one here, and you can see that by far the greatest amount of mass loss is contributed by the Arctic sea ice. So the Arctic sea ice has declined by far the greatest of all these ice sources. So we next look at the Arctic sea ice, and that is the Arctic summer sea ice recorded in September, the sea ice low. This is from that IPCC 2019 assessment on the cryosphere and the oceans, and the record runs from 1950 projected up to 2100. Here I've cut it back from 1950 to 2050 and made the observed recorded change in Arctic sea ice extent more obvious. In the IPCC report, this change was recorded by percentage change. So it has been declining at an accelerating rate, which is fairly clear there, and this is confirmed by NOAA's NOAA's Arctic report card of 2020 that gave the trend for the summer minimum sea ice in September per decade. So next is ice sheet melting. Remember that we saw that sea level rise has accelerated due to the combined increased ice loss from the Greenland and Antarctic ice sheets, and that mass loss from the Antarctic ice sheet over the period 2007 to 2016 had tripled relative to 1997 to 2006, and that the mass loss for Greenland doubled over this same period. This shows the Greenland and Antarctic ice sheets. This is a paper published in 2020, and the paper is titled Ice Sheet Losses Track High-End Sea Level Rise Projections. This is the worst case scenario, and there's a middle scenario and there's the best case scenario. On the vertical axis is melting of the ice in terms of sea level contribution rise. And so the mass is melting on the worst case scenario. This is Greenland. Greenland ice sheet mass loss is tracking the worst case scenario. This is from the IPCC, that 2019 special report. This is from 1950 up to 2100. Again, the ice sheet mass loss is expressed as equivalent sea level rise in meters. Here I've cut it down from 1950 to 2050, and the purple is the observed recorded Greenland ice sheet mass loss, and that appears to be tracking above the combined best case worst case scenario, and therefore on towards the worst case scenario. This is also from the 2019 IPCC report. This is the Antarctic ice sheet mass loss, and I've cut it down similarly from 1950 to 2050, and there is the purple historical recorded Antarctic mass loss, and that certainly appears to be tracking above the best case and towards the worst case scenario. And so to finish off with, we can make a summary of the findings on these many global climate change indicators, and in general, overall, they are all at record adverse highs, and they are all still increasing. We started with global emissions, Cumulative CO2 emissions are accelerating on the worst case scenario. CO2 equivalent emissions, that's CO2 accounting for methane and nitrous oxide, are accelerating on the worst case scenario. Atmospheric greenhouse gas concentrations, again a CO2 equivalent, accelerating on the worst case scenario. Radiative forcing, which is heat forcing, it's the total amount of heat that has been added to the climate system or our planet from the accumulation of greenhouse gas emissions in the lower atmosphere. That is accelerating from 1900 with a big increase from 1960 on the worst case scenario. Global surface warming, global average surface temperature increase is accelerating on the worst case scenario. Human emissions only, warming from human emissions only with the global warming index shows it's accelerating with a big increase in the rate of warming from 1960. Ocean heat is accelerating towards the worst case scenario. Ocean acidification is accelerating on the worst case scenario. Ocean deoxygenation is accelerating on the worst case scenario. The oceans therefore are in a terrible situation. Sea level rise is accelerating on the worst case scenario. And then we looked at the Arctic. Arctic heating is abrupt and appears on the worst case scenario from the one paper that looked at this. Then we looked at the overall recent study on melting ice, which showed that glaciers, Greenland and Antarctic mass loss is accelerating, and that the Arctic sea ice has lost the most ice compared to other sources. Last of all, we had the ice sheet mass loss from the IPCC 2019 special report, and that mass loss expressed as equivalent sea level rise. Greenland's mass loss is accelerating on the worst case scenario, and the Antarctic ice sheet mass loss is accelerating on the worst case scenario. So the overall situation is that all of these global climate change indicators taken together, they are at record highs. They are tracking the very worst case scenario, and they're accelerating.